All right, we're going to start the next session. It is new experimental investigation of LENR in various materials with UHV linear accelerator. And Natalia will be making that presentation. Natalia?
Okay, thank you very much. My name is Natalia Targosz-Sleczka, and I will present the new experimental results for accelerator-driven experiments at the University of Szczecin in Poland. And my group is shown over here, so I am only a small part of this large group. We almost all have something to tell you here at the conference, so please stay at the later part of this session and also visit our posters to learn more about what we do. I want to tell you that for over 25 or 30 years, we have studied low-energy nuclear reactions with accelerator-driven experiments, especially taking into account the so-called electron screening effect that enhances the cross-section for lowering projectile energies. I will try to explain it in details later on. This effect is especially important for deuteron-induced reactions in metallic media because there the electrons, the free electrons of the media, can actually help to enhance the cross-section. So the probability for such a nuclear reaction is then much stronger. We also expect that metallic structures loaded with hydrogen can be enhanced, so the nuclear reactions that are taking place in such structures can be strongly enhanced also at thermal energies. Of course, we are not able to check that experimentally with our accelerator, but we will show you some results that are very promising, and I hope to convince you that for thermal energies this is also important. So our goal, because this study has been performed for over 25 or 30 years, our goal is now to find a specific material or few materials that can be used for gas loading experiments, so the experiments in which you all know that the anomalous excess heat is being generated. So I will present only some results for DD reaction in few materials at energies ranging from 1 to 20 keV in our improved laboratory conditions that I will mention later on. If we want a nuclear reaction to occur, we need to collide two nucleons, so they need to come very close to one another. And to do that, they need to overcome the Coulomb barrier, which is regularly very high. And this means that the process is not so often, okay? It is a hard process to find this nuclear reaction to occur. It is probable, and there is this enhancement of this process possible due to so-called tunneling effect. And this tunneling is the probability for one particle to overcome this potential that is shown over here. Okay, so this is the Coulomb potential, and in normal conditions where two nuclei meet in a vacuum, let's say, the Coulomb potential looks like this. So this is the higher line. I don't know if you can see it clearly. So it's generally pretty high and broad, and the probability is then being described with such a factor, which is called the penetration factor. It gives you the probability of tunneling through this barrier. We have this EG over here. This is the Gamow energy, which is describing the height and width of this specific barrier. And for nuclear astrophysics, this is the place where I come from, We also define so-called cross-section with the astrophysical S factor that is shown over here. And then the cross-section is the product of this S factor and the exponential function that describes the probability of the tunneling. If then the same reaction takes place in a metallic environment, for example, we have the situation that is changed and shown here in this green box. So our electrostatic potential has to take into account the screening function over here. And if this is expanded into Taylor series, we can define something that is called the screening energy with the screening length over here. And we have the charges of two reacting nuclei that defines this specific screening energy. Then the penetration factor also changes, and it is shown over here. We have to include the screening energy, we have to include the screening energy over here. And the cross-section is also corrected with this factor shown here and here at the end. So what we do in our experiments, we usually take metallic target, which we deuterize first with deuterons, and then with the beam of deuterons, we try to follow this DD fusion reactions. We find the products of those reactions, and from the products, we can say what is the enhancement factor from which we can define the screening energy value. This is important because this barrier gets reduced, okay? So an electron cloud is being formed while this reaction is taking place in a metallic media. The electron cloud is being formed. The negatively charged electrons are attracted by the positively charged ions that react with each other. And this means that the Coulomb barrier can be reduced in a form as you see here on the picture. And what people usually do is they are trying to figure out what is the cross-section for the high energies, because this is the easiest part in the accelerator studies, because then at higher energies, the cross-section is pretty high, okay? So if we are above the Coulomb barrier, then the probability of such a reaction is very high. If we go down to lower energies and we go down below the Coulomb barrier, then the cross-section drops drastically, as you see over here. So if we will only check the cross-section for higher energies and then extrapolate down to low energies, we might miss some important phenomena that can occur over here. So this is for us especially important to actually check what is the real experimental cross-section at low energies to fully understand what is the structure there. I would like to mention very briefly that this electron screening effect was firstly introduced for dense astrophysical plasma. You see the first paper cited over here. In astrophysical plasmas, it can really change reaction rates by many orders of magnitude. Then for laboratory investigation, it started for gaseous targets, and there was theoretical description for gas, and then experimental observation in a gaseous target performed as the first one. And then enhanced electron screening coming from the free electrons when the reaction is taking place in the metallic media. This was firstly investigated by Professor Czerski's group and also independently by Professor Skasagi's group. Since then, there are many different materials that have been studied. It allowed for systematic study of target material dependence of this screening energy. You can see here screening energy versus the material given with the atomic number. But if you have a closer look on this plot, you will see that there are huge differences for the same material, the values can vary very much between one another, depending on the conditions in which the experiment was done, the data analysis, and other things. But we also found out in our studies that every contamination and every change of the crystal lattice can actually be crucial for the determined screening energy. So this is a spectra of Auger electron spectroscopy. And here you can see in black there is this virgin target, so clean target, freshly put into our system. And then after 4 hours, we have measured the Auger electron spectra, and it looks like this red line where you can see also contaminations coming from carbon and oxygen. And these might be good or bad. It depends on the amount of them, actually. So we don't know exact values that are helping or destroying the effect. But you can see also on the plot that is shown over here that for the clean target, the screening energy that is shown is fairly stable. Then, when we have a few hours of the measurements going on, so this is after 4 hours, we have the peak over here, it means that we have some contaminations and layers that have built up upon our target. And this means that the screening energy was actually increased by the fact that there were some contaminations at the target surface. And then after reaching this peak, it then lowers because there are too many layers then for the incoming particles to actually go through this layers to provoke this de-diffusion reaction. So we know that the screening will vary if we take into account the crystalline structure, the surface, and the bulk changes. So this is something that we want to study more. Here I'm just showing different results from different groups. One of those whose screening energies are the largest. And you can see, for example, that for palladium, there are papers showing even 800 electron volts of screening energy for DD reaction. I focused here on DD because this was in my abstract, so I didn't go farther. I wanted to stick to this specific reaction. So 800 electron volts for DD reaction in palladium. I suppose this is Professor Skasagi's paper from 2002. But there are other targets that are also showing the high values of electron screening energy. So these are the possibilities to be then used maybe in gas loading experiments as the good material to be studied with some nice perspectives to be used. I want to tell you that differences between different techniques of experimental studies, between the different analysis techniques, this might all be very crucial for the determination of the screening energies. So it is very hard actually to compare different results coming from different groups and different experimental setups. And now I would like to show you our experimental setup. This is our accelerator shown over here. This is an ultra-high vacuum accelerator, which means that we can reach the pressure in the target chamber of the value of 10 to minus 10 millibar, or with liquid nitrogen cooling 10 to minus 11 millibar. We have an electron cyclotron resonance ion source over here that produces our beam, for example, of deuterons, but this accelerator is optimized for light particles and also for low energies. So this is not a regular accelerator used in nuclear physics, because usually people want to have as high energies as possible. We want to have as low as possible. So the beam comes in. We have an analyzing magnet that allows us to pick specific beam composition, and then the beam goes to the target chamber that is over here. In the target chamber, we have the target holder that is connected to current integrator, so we know how many particles went in. And we also have there the detector, silicon detector usually, to find the products, charge products of these reactions that are shown over here. So we can find protons, tritons, and helium-3, and this is a sample spectrum. As Professor Kasagis says today, the regular one, so the nice one, okay? So this is the, what we got from the latest experiments. And these are the results. So I want to show you the results for zirconium, deuterated target, and also titanium palladium. This is an alloy, both for DD reactions. And you can see here the experimental points. We have the blue ones are the atomic beam ions, so D1. The green ones are D2+, and the red ones are D3+. We had to pick specific beamline to reach lower and lower and lower energies, because it was the only way that the accelerator was working stably, let's say. So, and for this data that you see here, we have a fit in blue line, and this is one parameter fit, which gives us the screening energy. For zirconium, it is 350 electron volts in the energy range of the impinging particles between 1 keV and 20 keV. For titanium palladium, and we wanted to study this target because there were papers that showed that titanium doesn't really have huge screening. So we wanted to confirm that. And we wanted to add something more to it. So we added only a slight amount of palladium. I think it was 5% atomically. Generally, this is titanium target, okay? The palladium is only, let's say, small contamination here. And for the same kind of experimental points, we also have this curve here, and the screening energy is equal to 25 electron volts. This measurement was done for projectile energies between 2.5 keV to 20 keV. And now I want to ask this question, are these correct? So what can we understand from that? And I want to tell you that from our experiments, we really see very different screening energies if we take, for example, zirconium. This is our best known, let's say, material. We really studied this material for many years in many conditions. And we could define or determine experimentally screening energy values for zirconium from 100 electron volts to 500 almost, okay? So it's a huge discrepancy. So which of the value is correct? Where do we make mistakes? And I want to tell you that there are no mistakes here. The differences occur because there are different metallic structures involved in the different experimental trials. So it is all connected, as we understand now, to crystal defects that are really playing the crucial role in determination of the screening energy. So I want to mention that Mathieu will talk about this in details just after me, so I will not go into details here. But I want to say that this crystal lattice defects can really be important for determination of the screening energy. And it can be fatal, or it can be very positive for the energy that we want to determine. The deuteron beam itself can produce very different phenomena on the target surface and in the bulk. And you can see over here the pictures of a target on the, which is this is the left-hand side. Okay, so here you can see the target that is clear, freshly prepared. And on the right-hand side, you can see the target that has been implanted with deuterons. So you can see that the surface is changed dramatically, right? So this is something that is really important to understand. And deuteron beam itself can produce vacancies in this sample that we study. And it also produces, when the deuterons are already inside, it also produces diffusion of these vacancies towards the surface. We also see some effects of carbon and oxygen, but I will let Mathieu to talk about this in details. So in summary, I would like to mention that we have performed some experiments at the University of Szczecin using our accelerator to determine which target is good or bad for further studies in gas loading experiments for the generation of excess heat. And for zirconium, we determined the screening energy value of 350 electron volts. For titanium palladium alloy, it is low, it is only 25 electron volts. We will follow with the studies considering different targets. We want to check also the screening energy value for the layered target of nickel copper that the society uses in many different experiments. We want to check other alloys and maybe find some conditions which we will be able to control, because now it seems like we understand the influence of the conditions, but we cannot really control them during our measurements. So the last point is that the crystal lattice defects have the influence on the effective electron mass, and it means that it can actually change strongly what is connected to determination of the screening energy. Okay, thank you. Merci.
Yes, sir.
Yeah, very nice data from the very low energy experiment, which I wanted to do that. Congratulations to the Szczecin group.
Thank you.
And my comment, one comment is, you said the strongest screening energy found by our group, but that is not. 800 electron volt is not from ours.
Okay, sorry.
For the palladium, I have just 300 electron volt.
Okay.
But palladium oxide makes 600 electron volt. Okay,
yeah, and there was also palladium lithium, but this was another reaction, right?
Yeah. And then my question is, how much energy, I mean minimum energy you can do the experiment by your equipment? This is one point. Lowest energy is...
Lowest energy. Right now, it was 1 keV, but we had some, also we had some, tests for lower, and I think we can do more, but the stability of the system is then not so great. So this will be an effort, but we want to go down below 1 keV, yes.
Okay. And then I always said, don't forget the effect of how to say, cooperative colliding mechanism of a DD reaction using the molecular beams.
Okay, yes. We have taken this into account, and also, if I can mention, because I didn't do that, and this is something that I should have. So there are these plateaus over here Konrad will talk about them, okay? So I don't want to spoil his talk.
Okay.
But these are very important for our studies, so I hope that you can stay and listen to his talk as well.
Okay, thank you.
Thank you.
Yes, sir.
Yeah. Thank you for the presentation. Wonderful. I have a question about the targets that you used. You said that the features on the surface are important, crystal defects, but is it only the feature or also something in the bulk?
Yeah, the bulk as well, yeah.
Okay.
It will be the surface and the bulk, and Mattia will give you the details
thank you.
soon. Yeah, but
you very
in the metallic target, the whole, I mean, until the neutrons reach the density, the depth, right? It all matters what's
Okay.
going on inside. Yeah.
And also, how do they look like, these targets? Are they
Yeah, these are metal plates.
Just plates?
Yeah,
Okay.
plates, very thin and yeah,
Okay.
regular, nothing special. But also Mattia will talk
Thank you.
about this.
Thank you very much.
Sure.
Are there any further questions?
I have
Yes. Francesco?
thickness of your target.
Yeah, it's usually around 1 millimeter thick, but it depends on the specific sample. Yeah.
Very thick.
Yeah.
Okay, thank you.
Emanuele?
You used the titanium palladium alloy, and I looked that the phase diagram is quite complicated. So do you know if that alloy is the same has the same structure of pure titanium, or is a different?
Yeah, mostly so. But to be honest, I'm not the specialist, so maybe Mattia can comment on that.
So it's a 0.5%. Yeah, so it's T alpha.
All right, thank you, Natalia.
Thank you.